Now we will discuss one of the most important parameters, which is the voltage regulation. Now the transformer, it will have an impedance associated with it, right? On one side there will be the input voltage V1 and on the other side you have the output voltage V2. Now what happens, depending on the current that is flowing through this, the voltage drop will vary. Okay, now for a constant input, V2 will now vary with the load, right? The load is going to be connected at the output side, and depending on the load, the current will be drawn, and depending on the current, the voltage drop will be increasing. As current increases, voltage drop increases. That means V2 will keep reducing. So this variation of the output voltage with respect to the variations in load, that is measured by means of voltage regulation. We don't want too much variations. So percentage voltage regulation, this is expressed as the voltage that is available at no load condition minus the voltage that is available at full load condition. That means when the full rated current is flowing, as a percentage or as a fraction of the full load voltage, and into 100, because we are talking about percentage voltage regulation. Now how do we want the voltage regulation to be? It should be less or it should be more for good performance. So from the expression you can see that it is the drop as a fraction of full load. We don't want too much drop, right? That means the voltage regulation should be as less as possible. Okay, so that ensures that it is a better performing transformer. So lower voltage regulation implies better performance. This is the desirable condition. So this is one expression. We can also express in terms of the current and the impedance value. So if you are taking this impedance value to be R plus jx, let us say, then what will be the no load voltage? No load means there is no current flowing. So in that case, V2 will simply be equal to the input voltage V1. So if we substitute the same in this expression, you are simply going to get V1 minus V2 at full load condition, right? So you can write voltage regulation is equal to V1 minus V2 full load divided by V2 full load. Now the voltage drop you can write as I into R plus jx, but we don't want in terms of the phasor. So what we will do, we can make use of the phasor diagram. If this is the full load voltage, okay, and at a particular power factor, say phi, the full load current is having this magnitude, then what will be the drop across resistance? The drop across resistance will be parallel to the current, and the drop across the inductance, it is going to be leading by 90 degrees, and this is the V1. Now the phase difference between V1 and V2, this is going to be a very small value, okay. So if you just extend this and drop a perpendicular from this and this is going to have almost the same magnitude, because this angle is very, very small. Now this is 90 degrees and this is also 90 degrees. So what will be the magnitude of this? This angle will be phi. So this you can write as I2FL into R cos phi. And what about this magnitude? Here if it is phi, then this angle is going to be 90 minus phi. So this will also be 90 minus phi. So this angle is going to be phi. So you can mark phi here. Then this value is going to be I2FLX into sin phi. So from phasor diagram, you can take this as delta. Considering delta is very small, this implies that V1 is approximately equal to the full load voltage V2FL plus I2FLR cos phi plus I2FL x sin phi. So what will be V1 minus V2FL? This is approximately going to be equal to I2FL, you can take out common. So R cos phi plus x sine phi. Okay. So now what will be the voltage regulation? You can write the percentage voltage regulation. It is going to be I2 full load current into R cos phi plus X sine phi divided by V2 full load. Now here you got a plus sign for lagging phase. If it is a leading phase, if the load current is leading by 5 degrees, then you can write the negative sign. Okay. So plus is going to be for lagging load, while negative is going to be for leading load. Okay. So this is into 100. Don't forget into 100 because we are talking about percentage here. Okay. Now another thing that you can see here is this V2FL, this I2FL if you are bringing to the denominator. In the denominator you will have the full load voltage divided by the full load current, right? Usually we take the full load or the rated values as the base values. So in the denominator you are going to have a base impedance. Okay. So percentage voltage regulation, once again you can write as R divided by the base value of impedance into cos phi plus or minus X by the base value of impedance into sine phi. This is into 100. Okay. So why did we write this? Because V2 full load divided by I2 full load is nothing but V2 base divided by I2 base, which is the base value of impedance. So that means voltage regulation will be in terms of the per unit value, R per unit cos phi plus or minus X per unit sine phi into 100. Okay, so this is in terms of the per unit values. If you have the per unit values of resistance or the impedance of the transformer, then you don't need the voltage or the current to find the voltage regulation. Now instead of writing R per unit all the time, we will make use of the small letter. That means R per unit I will write as small r, and X per unit I will write as small x. Okay. And one more point that you can consider here is phi, if you are taking without the sign, then you have to use this negative sign. Okay. But if in case the load is a leading load, then sine phi is automatically going to become negative because phi itself will have a negative value, right? So you can use the expression r cos phi plus x sine phi, okay, directly. You don't have to worry about the negative sign. Now the maximum and zero voltage regulation conditions. What is the condition at which maximum voltage regulation will occur and zero regulation will occur? Maximum voltage regulation is not desirable and zero voltage regulation is desirable. First we will discuss the maximum voltage regulation. So this is with respect to what? With respect to the power factor, okay, at which power factor maximum VR will occur. So we have to differentiate with respect to phi and equate it to 0. So dVR by d phi, this is equal to 0. Now if you substitute the expression for the voltage regulation, you are going to get R cos phi plus X sin phi. So we are assuming that the phi is taken care of by the variable itself. That means phi will have magnitude as well as the sign. So if it is leading, phi will automatically be negative and sin phi will come out to be negative. Okay. So if you are differentiating this, then what you are going to get? R minus R sin phi plus X cos phi is equal to 0. This means that tan phi is equal to X by R. This is the condition for maximum voltage regulation. You can see that the impedance angle, if impedance triangle if you draw, this is going to be X, R and Z, and this is theta, right? Impedance angle. But you can see tan phi is also equal to X by R. That means phi is equal to theta, right? So that point also you can write. Implies phi is equal to theta, that is load power factor angle is equal to the transformer impedance angle. Okay, impedance of the transformer. So this is one important point, and another important point that you can see is X and R, they are both positive values. That means tan phi is a positive value. That means phi should be positive. If tan phi is positive, then phi is positive, right? So phi is positive means it is a lagging load. Okay, since tan phi is equal to X by R is greater than 0, this implies phi is greater than 0. This implies it is a lagging load. Okay, so that means the maximum voltage regulation will occur at a lagging load. Okay. Next, zero voltage regulation. So this is pretty straightforward. When will you have zero voltage regulation, right? So you can simply equate the voltage regulation to 0. R cos phi plus X sin phi is equal to 0. This means that tan phi, here you are going to get minus R by X. Okay. So you can see here that there is a negative sign here. R is positive, X is positive. So tan phi is a negative value, which means that phi is a negative value. Tan phi is equal to minus R by X is less than 0. This implies phi is less than 0. That means it is a leading load. So this implies that zero voltage regulation will occur at a leading load.